We are on to section 3 here, and section 3 for this unit is the application of our parametrics. So let's get started and fill in a couple spots here. So um, as we've seen before, I'm sure you've seen it in physics and other classes, we want to know about the gravity constant for metric, the most common in physics class. That's 9.8. I used 9.81 actually. And some of you may know this, probably not all of you, but there's also like a feet per second squared, so the US customary unit gravity constant, and that is actually 32.2. So we just want to fill those in because we'll be using those for our equations. So when we look at these problems, it's no different than the other problems we've done in the other two sections, but rather than just being given the equations for x, the x parameter and the y parameter, we have to create the equations based on the story or the story problem that is given. So we did the Wile E. Coyote introduction, and we talked about how we can break vectors into x and y components and then use gravity equations to determine certain things about the path that the object would take. So here we have a steel projectile, example 1. It is shot horizontally from a 30-meter high tower. So make sure we get our picture drawn. So here's our tower. And I'm just going to draw the arrow out. So it is shot horizontally, that is 40 meters per second. And that's 30 meters high, it says. And that's all we got. That's the only information we're given. So let's see what we can do here. If we look at this box up above, again, from the Wile E. Coyote scenario and from class discussion is the introduction to this applications, we know that there's some information in the x position that we can use here. So what we use is the initial velocity times cosine of theta, and then that times t give you position, because if you have velocity times time, v sub 0 times time, you get position. So our v sub 0 is 40. Now cosine, what angle do we use here? Well, our angle we use is 0 because we're just shooting the projectile horizontally. So that's 0, and then if we were to shoot, like if here's the horizon, we may instead fire the projectile at some angle and then hit down. But here we're just sending it horizontally. So cosine of 0 is 1. So we take 40 times 1 times t, we get 40t. And then that's the only components of the x parameter. So let's look at our y. Our y says let's start with our h sub 0, h sub 0 being the initial height. So there we have 30 meters plus, now we have v sub 0 times sine theta. Well, if sine of theta, well, I guess I'll write it out, but 40 is our initial velocity. Sine of 0 is 0. And then we take it times time. So that, in the end, that whole thing runs to 0 because anything times 0 is 0. So, and then this equation is very generic. 1/2 g times t squared. Well, the 1/2 is the constant. G is the gravitational constant. So here we have 1/2 of g, which is where we say minus 4.9. Half of that. times t squared. We have our position in the x and our position in the y. The things that affect the position horizontally is just that horizontal velocity. In the y direction, vertically, we have our starting height affects the position. The velocity vertically doesn't, because it's just sent horizontally, we don't get any vertical component. The other thing that affects the position of the object vertically is gravity. So the question is asking how far from the base of the tower does the projectile hit the ground? And this is where what we determined is if we have an object that let's say we free fall, we just drop the object from the edge of the tower here. If we drop it from 30 meters, it's going to have a certain amount of time that it's in free fall. And we'll look at a Mythbuster video that proves this, but the amount of time that an object is free falling vertically here, if I just drop the object, that is the same amount of time, even if we were to send this object horizontally at 40 meters per second and we were to shoot it out horizontally, the amount of time in the straight vertical free fall, that is the exact same amount of time that this object would take to get to the ground, that it was shot horizontally. So what we can do, we can use this information and we can say, well, if we know how much time the object takes to go in free fall vertically, that same amount of time can be applied to the horizontal position. And so we can take 40 times that time that we're falling vertically and figure out how far we went horizontally. So let's figure out how much time were we in free fall vertically. Well, we have a y and a t, but we only have one equation here that we want to solve for. So what we can do is we know that after the time we're looking for is the time when the object hits the ground. And that is represented by y equals 0, because that's the position of the projectile after that certain amount of time has passed and it has hit the ground. So if we set y to be 0, 30 minus 4.9 t. See, now we can find t because we have one equation and one unknown. So if we take and move one of the terms, doesn't matter, over 4.9 t squared is equal to 30. Divide by 4.9 and we get t squared is 6.12. We take the square root and t equals about 2.47 seconds. I'm going to label that with units of seconds. So we now know that this object falls for almost 2.5 seconds vertically. And it goes to reason then that the object is also traveling horizontally for 2.5 seconds at 40 meters per second. So we can say that x is 40 times 2.47. So the x position is 98.97 meters. And to answer the question is from the base of the tower. So we can apply the same process over and over and over. If you look at our examples in particular, next video I will actually show you how to do this in the graphing calculator. But if you look at these, same problem, example 2, are traveling 15 meters per second. So that's a horizontal 15 meters per second off of a cliff that is 55 meters. How far from the base of the cliff does the car strike the water? Sounds a lot like example 1, right? So we would set it up the same way as example 1. Example 3 is a little different because rather than finding how far from the building it lands, this time we know how far it lands. The question is, how high up was the object released? So, anyways, I'll stop there and we will continue on from other examples and maybe some calculator usage too.